Japan and Europe are positioning themselves as world leaders in magnetic fusion research. Japan has just created something mind-blowing. A machine so powerful it can heat things up to 200 million degrees Celsius, called the JT60SA. It's essentially a mini-sun, outfitted with an advanced magnetic system featuring 18 massive coils and a central solenoid, all kept cool with liquid helium to manage the extreme heat. However, if not handled carefully, this powerful machine could lead to a catastrophic outcome. If something went terribly wrong, could we really manage the fallout of handling such intense forces? From 2021 to 2027, Europe will invest around €6 billion in fusion development. Let's dive into the potential dangers of harnessing this incredible power. Fusion energy is like the holy grail of power sources, virtually limitless and remarkably clean, unlike its cousin nuclear fission, which works by splitting atomic nuclei. While fission breaks things apart, fusion mimics the sun's process by combining atoms to release an immense amount of energy. The magic happens inside devices called tokamaks, which are experimental reactors resembling something out of a sci-fi movie. These high-tech machines are designed to create and study plasma that's so hot it makes the sun look cool in comparison. Due to the incredible potential of this process, scientists from around the world are uniting, each contributing their piece to this massive fusion puzzle. There's the colossal ITER project in France, which is a major player in the fusion research field, along with smaller, highly focused experiments popping up everywhere, from the US to China and Europe. Researchers are working tirelessly, developing innovative methods to turn this futuristic vision into reality. However, among these global efforts, Japan's JT60SA stands out as the most remarkable project of its kind. What makes the JT60SA so special? It's pushing boundaries that even seasoned scientists find impressive, standing out as a high-performance machine in a field filled with incredible advancements. While other projects are significant and essential, JT60SA is where things truly get exciting, promising breakthroughs that could revolutionize energy as we know it. In an unexpected move, just a day after the official opening of COP28, where countries gathered to discuss reducing fossil fuels, Europe and Japan unveiled the JT60SA. This cutting-edge experimental device, the most powerful of its kind to date, represents a landmark achievement for policymakers, scientific communities, research organizations, and industry. At a ceremony held on December 1, 2023, European Commissioner for Energy Kadri Simpson, Japan's Minister for Education, Culture, Sports, Science and Technology Masahito Moriyama, and Japan's Minister of State for Science and Technology Policy Sanai Takaichi joined senior politicians, industry representatives, and researchers to inaugurate the JT60SA facility. From the control room, they witnessed a plasma operation, marking a significant milestone in the project's timeline. JT60SA is a product of the Broader Approach Agreement, a scientific collaboration between the European Union and Japan to advance fusion research through various projects. Construction began in 2007 and was completed in 2020, with further technical improvements leading to its first plasma operations toward the end of 2023. The total cost for construction was around €560 million, shared between Europe and Japan. This project exemplifies science diplomacy and is praised for its collaborative spirit, efficient management, and exemplary execution. Unveiling JT60SA during COP28 sends a strong message about energy's future as the world faces climate change and the need for sustainable solutions. Fusion energy offers a promising alternative, positioning Europe and Japan as leaders in transitioning to cleaner energy sources. The powerhouse of JT60SA is part of Eurofusion, a collaboration that unites about 170 laboratories and industrial partners from 29 countries, resembling a big team of scientists and engineers all focused on the success of JT60SA. Eurofusion, which includes a consortium of 31 European laboratories, has significantly contributed personnel and equipment, while Japan's National Institutes for Quantum Science and Technology, QST, played a crucial role by providing essential resources and expertise. So, what exactly makes JT60SA special? It uses the latest plasma control technologies to ensure smooth operation, akin to a symphony where every instrument plays in perfect harmony. JT60SA achieves this with advanced heating and current driving systems that work alongside various control tools, such as magnetic coils and extra heating mechanisms, to fine-tune the plasma's shape and stability. Precise control is crucial, as a plasma imbalance could lead to disastrous outcomes. The JT60SA's technology maintains optimal plasma conditions, making fusion energy generation viable. JT60SA isn't just tackling today's fusion challenges. It's also a platform for future innovations, acting as a long-term research environment rather than a one-hit wonder. It aims to pioneer new methods for controlling plasma, an essential component for fusion. By experimenting with various techniques, JT60SA strives to make reactors more efficient and reliable, essential steps toward powering our future. The JT60SA project plays a key role in the global fusion energy quest. Its breakthroughs are shared with ITER, another fusion giant, to tackle challenges and improve processes, accelerating fusion science's progress. This teamwork advances fusion science, bringing us closer to the day when fusion energy powers our lives. By perfecting these technologies, JT60SA is laying the groundwork for a future powered by clean, sustainable energy. JT60SA is reshaping nuclear fusion by constantly evolving to keep up with ITER's latest discoveries. Initially, its primary goal was to support ITER, but now JT60SA is looking ahead to meet the requirements of future fusion reactors. Its focus has shifted to enhancing steady-state operations and exploring new plasma scenarios to handle the conditions anticipated in future fusion power plants like DEMO. This international collaboration, especially between Europe and Japan, is essential not only for overcoming technical and logistical challenges but also for building a strong team of skilled researchers and engineers essential for future fusion projects. JT60SA is more than a research facility. It symbolizes future energy. Using advanced superconducting magnet technology and cutting-edge plasma control systems, it sets a high standard for future projects. This facility demonstrates fusion energy's immense potential to become a limitless, sustainable power source. However, the journey doesn't stop here. As JT60SA continues to evolve, it will greatly enhance our understanding of plasma physics, moving fusion from theory to practical reality. Furthermore, the energy required to initiate and sustain fusion reactions is substantial. Efficient energy delivery systems and energy recovery technologies are essential for optimizing the overall energy output of a fusion power plant. The quest for fusion energy has united scientists and engineers from around the world. International collaborations such as the ITER project pool resources and expertise to tackle the immense challenges associated with fusion research. A diverse range of approaches, including tokamaks, stellarators, and inertial confinement fusion, are being explored to find the most promising path to commercial fusion power. Recent advancements in materials science, supercomputing, and plasma physics have accelerated progress in fusion research. The achievement of net energy gain in a fusion experiment marks a significant milestone, demonstrating the feasibility of harnessing fusion energy. However, scaling up fusion reactors to commercial power plant levels will require continued innovation and breakthroughs. The potential benefits of successful fusion energy are immense. A virtually inexhaustible, clean, and safe energy source could revolutionize global energy systems. Fusion power could significantly reduce greenhouse gas emissions, mitigate climate change, and provide energy security for nations worldwide. While challenges persist, the long-term vision of a fusion-powered future is inspiring. Continued investment in research and development is essential to overcome the remaining obstacles and unlock the full potential of fusion energy. Overcoming challenges in the pursuit of fusion, the journey to realizing fusion as a practical energy source has been marked by significant challenges. The JT60SA reactor, a cornerstone in this pursuit, epitomizes the complexities involved. Undertaken as a classified project in the mid-1980s, this ambitious endeavor required a complete rebuild from scratch. Despite being considerably smaller than the ITER project, the JT60SA is a formidable machine capable of containing 135 cubic meters of plasma. Data generated from its operations is invaluable to the broader fusion community, including the ITER project. Development of the JT60SA was a protracted process, significantly exceeding initial timelines. A myriad of challenges, from supply chain disruptions to the need for seismic upgrades following the devastating 2011 Tohoku earthquake, contributed to the extended project duration. The complex engineering involved in constructing and operating such a massive machine inevitably led to unforeseen setbacks. A critical incident involving a short circuit and subsequent helium leak in a superconducting magnetic coil highlighted the inherent risks and challenges associated with fusion research. Beyond the technical hurdles, the human element is integral to the success of fusion projects. The dedication and resilience of the teams involved are essential in overcoming setbacks and maintaining project momentum. The near disaster involving the cooling system leak underscores the high-stakes nature of fusion research and the unwavering commitment of the scientists and engineers involved. The JT60SA project serves as a testament to the complexity and perseverance required to advance fusion technology. While challenges abound, the potential rewards of successful fusion energy are immense. A clean, safe, and virtually limitless energy source could revolutionize human society and address pressing global challenges. The broader fusion landscape, the JT60SA, is one piece of a global puzzle. Numerous countries and institutions are engaged in fusion research, exploring various approaches and technologies. The collaborative nature of this field is essential for sharing knowledge, overcoming challenges, and accelerating progress. As research progresses, it is becoming increasingly clear that fusion is not solely a scientific endeavor, but also a significant engineering and economic challenge. Developing cost-effective and scalable fusion reactors will require innovative solutions and substantial investments. Despite the complexities and setbacks, the pursuit of fusion energy remains a compelling goal. The potential benefits for humanity are too substantial to ignore. With continued dedication, international cooperation, and technological advancements, the dream of harnessing fusion power may one day become a reality. A near-catastrophic incident involving electrical insulation necessitated a prolonged repair process, underscoring the inherent risks associated with large-scale experimental facilities. To mitigate future occurrences, rigorous testing protocols for reactor components have been implemented. But the challenges aren't limited to engineering and safety concerns. The decision to exclude tritium from the JT60SA experiment simplifies certain aspects of the reactor's operation, but it comes with its own set of implications. Tritium, a heavy isotope of hydrogen, is a crucial ingredient for achieving efficient fusion reactions. Without it, the reactor can't fully replicate the conditions found in stars, where fusion naturally occurs. The significance of tritium in fusion research cannot be overstated. As a powerful energy source with unique properties, tritium is essential for generating electricity through fusion. The ITER project, with its planned integration of tritium by 2035, represents a major step forward in harnessing this vital element. Tritium's role is indispensable not just for its energy potential, but also for its ability to make fusion reactions more efficient and practical. Japan has set its sights on achieving commercial fusion power by 2050 through the DEMO project, underscoring the nation's commitment to leadership in this field. Transitioning from experimental reactors to a power plant capable of producing net electricity is no small feat. Successfully managing the tritium fuel cycle, ensuring plasma stability, and developing advanced materials capable of withstanding extreme conditions are key challenges that must be addressed. In essence, JT60SA is a cornerstone of global fusion energy efforts. By sharing its findings with ITER and contributing to international research, it accelerates fusion technology development. JT60SA is designed to harness the sun's power by replicating its energy-generating process. At its core is a donut-shaped chamber where extremely hot plasma is contained. Powerful magnets keep this superhot gas under control. JT60SA is a groundbreaking achievement and the world's largest and most advanced fusion reactor, critical to the global effort to develop fusion energy, as exemplified by the ITER project in France. By studying plasma behavior in JT60SA, scientists gain valuable insights into the complexities of fusion. A major milestone was reached on October 26, 2023, when JT60SA successfully generated its first plasma after nearly 15 years of development, marking a huge step forward and confirming the reactor's functionality. Project manager Sam Davis and the EU's Fusion for Energy Organization, working closely with Japan's QST, are thrilled with the results. The science behind JT60SA is based on nuclear fusion, which involves combining two lightweight atomic nuclei to form a heavier one, releasing tremendous energy. Achieving this requires creating plasma, a superheated state of matter. Successfully controlling this process is a monumental challenge, but it promises virtually limitless clean energy. While creating the first plasma is a significant accomplishment, scientists still face obstacles in sustaining this powerful reaction. The journey toward fusion energy continues, with JT60SA moving us closer to a future powered by the sun's energy. Plasma is often called the fourth state of matter, behaving differently from solids, liquids, or gases. Unlike ordinary matter, plasma consists of highly energized particles, ions and free electrons, that give it distinctive properties. Imagine a gas heated to extremely high temperatures where violent molecular collisions strip away electrons, creating a charged particle soup known as plasma. Our Sun is a massive plasma sphere where atomic nuclei, mainly hydrogen, move at incredible speeds under millions of degrees Celsius, colliding to form helium and releasing enormous energy. This process, known as nuclear fusion, is the reaction scientists hope to replicate on Earth. The potential of fusion energy is vast, offering a nearly inexhaustible, clean, and safe energy source. Unlike traditional nuclear plants that rely on fission, splitting atoms, fusion combines atoms and produces minimal radioactive waste. Scientists have pursued fusion power for decades, needing to recreate the Sun's extreme core conditions by generating temperatures in the tens of millions of degrees Celsius and confining plasma long enough for fusion reactions to occur. Containing plasma is one of fusion's biggest challenges. Due to its high temperature, plasma tends to expand rapidly. To prevent it from touching reactor walls, which would cool it down and dissipate energy, scientists use powerful magnetic fields. This is similar to how Earth's magnetic field traps charged particles in radiation belts. Researchers have explored several magnetic confinement approaches, including tokamaks and stellarators. Tokamaks, like ITER, use a combination of toroidal and poloidal magnetic fields to form a magnetic cage for plasma. Stellarators, though complex, offer steady-state operation, unlike tokamaks which operate in pulses. Despite the remaining challenges, fusion energy is a global priority. If successful, fusion could transform energy production, providing a sustainable, abundant power source for generations. While complex and ambitious, the potential rewards are immense. Achieving fusion energy on Earth is a monumental challenge, but its potential is vast. Compared to nuclear fission, fusion packs a larger energy punch, generating 4 times more energy per kilogram of fuel. This incredible energy density is a primary reason scientists are working tirelessly to make fusion a practical reality. Fusion power could transform our energy landscape by providing a virtually inexhaustible energy source. Most fusion reactors in development use tritium and deuterium, special hydrogen forms. Astonishingly, a few grams of these fuels could power a developed nation for years. The abundance of fusion fuel is another advantage. Tritium can be produced by combining fusion-generated neutrons with lithium, widely available, and deuterium is easily extracted from seawater. These fuels are practically unlimited, ensuring sustainable energy for millennia. Unlike traditional nuclear power, which produces long-lasting radioactive waste, fusion generates minimal waste, making it an environmentally friendly energy solution. Future fusion reactors are being designed with safety as a paramount concern. Unlike fission reactors, which rely on complex control systems to prevent meltdowns, fusion reactions are inherently self-limiting. If conditions become unstable, the fusion process simply stops, and the plasma fuel disperses harmlessly. This inherent safety makes fusion a promising candidate for a clean and secure energy source. Furthermore, fusion reactions occur rapidly, preventing the buildup of harmful byproducts. The risk of a runaway reaction, a nightmare scenario in fission reactors, is virtually non-existent in fusion. While the challenges of initiating and sustaining fusion are formidable, the potential benefits for the environment and human society are immense. Fusion energy offers the hope of a low-carbon future powered by a virtually limitless, clean, and safe energy source. Replicating the Sun's core on Earth is a monumental scientific and engineering challenge. While gravity compresses the Sun's matter to initiate fusion, terrestrial scientists must create these extreme conditions artificially to induce fusion reactions using deuterium and tritium. Temperatures exceeding 100 million degrees Celsius are required, far hotter than the Sun's surface. However, temperature alone is insufficient. Precise control over magnetic fields and pressure is essential. Maintaining plasma stability within these demanding conditions is crucial for sustained energy production. Current experimental reactors are making significant progress towards achieving these stringent requirements. However, substantial obstacles such as improving energy confinement and controlling plasma instabilities persist. Overcoming these challenges is pivotal for developing practical fusion power. Engineering and material science challenges also abound. Constructing a fusion reactor capable of withstanding and controlling such extreme conditions is an engineering marvel in itself. Developing materials that can endure these intense temperatures and pressures without melting or degrading is a formidable task. Additionally, the complex interplay between magnetic fields, plasma behavior, and reactor components necessitates sophisticated control systems and real-time diagnostics.